All right. Hello, everyone. We're gonna get started now. Just for like a quick schedule. Jason's gonna give a talk, and then we're gonna open it up to Q&A. And to introduce Jason, he's a research scientist at Meta Superintelligence Labs. Previously, he worked at OpenAI for 2 years, where he co-created O1 and Deep Research. Before that, he was a research scientist at Google Brain, where his work helped popularize chain of thought prompting, instruction tuning, and a lot of emergent phenomena. His research is some of the most influential in the modern AI world, with over 90,000 citations. And Jason, it's great to have you here today. Thanks for taking the time to speak with us, and take it away.
Yeah, thanks for a nice intro. Fun to be here. I guess today I'll try to keep it not too long, maybe like 25 or 30 minutes, and then we can do like a Q&A session on whatever you guys want. So I'll talk today about 3, I think, like pretty simple but maybe fundamental ideas to understand to like navigate AI in 2025. So I think if you ask this question of like how our world is going to change with the development of AI, you get sort of this like pretty broad spectrum of answers depending on who you ask. So one of my quant trader buddies says like, ChatGPT is cool and all, but it can't really do any of this stuff in his job. And then on the other end of the spectrum, you have people who, I asked recently an AI researcher at a top lab, and he says he thinks we basically have 2 to 3 more years of working before AI takes our own jobs. So there's sort of this huge spectrum of how people think AI is going to play out. And so I'm going to talk about sort of 3 ways of thinking about it. The first sort of trend to understand is basically that intelligence is going to become a commodity. And the sort of cost and accessibility of finding out knowledge or doing some reasoning is going to be driven towards 0. The second is something that I call verifier's law, which is that the ability to train AI to do a particular task is proportional to how easy it is to verify that task. And then the final one that I want to talk about is this sort of jagged edge of intelligence. So both the capability and the rate of improvement of AI on a particular task is going to vary based on certain properties of those tasks. So first let's talk about intelligence as a commodity. So I would say the way that I sort of think about it is there's 2 stages of AI progress. So the first stage is sort of when you're pushing the frontier. So AI can't really do the thing well yet, and you're sort of like unlocking that new ability. And you can see like, if you plot, for example, MMLU, which is a very common benchmark for the past 5 years, you'll see that you gradually make progress on the performance. And then the second stage of AI progress is sort of once you have an ability, it becomes commoditized. So here's an example where you can see the y-axis is time, and then you can see the cost of getting a particular performance on MMLU in like number of dollars. And you can see the trend is every new year, the cost of using a model with a particular level of intelligence decreases. And you might say like, why might this trend continue? And the argument that I would make is that it's the first time in the history of deep learning that adaptive compute actually like truly works. So if you look at maybe the whole entirety of deep learning up to like last year, we were in sort of this mode where the amount of compute you would use to do a particular problem would be fixed regardless of how hard the problem was, whether it was giving the capital of California or a very hard competition math problem. But now we're in this era of adaptive compute where you can vary the amount of compute used to do your task. And this was sort of first shown with O1, which came out more than a year ago now, which showed that if you increase the amount of compute used at test time to solve math problems, the performance on that benchmark is higher. And the reason why adaptive compute means that you can continue to decrease the cost of intelligence is that you don't have to keep scaling model size. So like if you have a very easy task, you can keep going to the limit of like how cheap of compute you'd have to spend to do that task. And the second part of this is you can think about what's the time to retrieve certain pieces of public information. So you can so on the x-axis here you have like pre-internet era, internet era, chatbot era, and then agents era. And then you can ask like how long does it take to find a certain piece of information. So for example, if you wanted to know like what was the population of Busan in 1983, before the internet, you'd probably, I don't know, have to drive to the library and then like look in a bunch of encyclopedias to find that. That might take a few hours. In the internet era, you'd have to like, I don't know, search, and then you kind of like browse the websites to find the one that actually gives you the answer, and that might take minutes. And then now it's basically instant to get that answer. And then you can ask like a progressively harder piece of knowledge, like how many couples got married in Busan in 1983. And then if you want to solve this before, you have to like probably drive to, if you don't live in Korea, you have to probably like fly Korea first, and you have to go to the nearest like I don't know, government library that like has like catalogs of this information. You'll probably like dig through like a few dozen books to find like that specific information. Internet era, it might be easier. You can like search it up, but like maybe you don't speak Korean, so you have to like look through all the websites and get someone to help you. In the chatbot era, it's a bit easier. And then with the agents era, I think this is like something that can be found within a matter of minutes. And then you can see the trend for even harder things. Like if you want to ask like, of the 30 most populated cities in Asia in 1983, sort them by number of marriages in that year. And I think that's something that can be done now maybe in hours, but pre-internet era, it would take like weeks to answer that question. Yeah, here's an example. So this is actually not a super easy question of like how many people got married in Busan in 1983. O3 was not able to do this, but OpenAI operator can do this because you have to go to this like database called COSYS, and you have to like click around until you get the exact database query that's correct, and then you can find the answer. And one way that we've tried to measure this at OpenAI is via a benchmark called BrowseComp, which just stands for browsing competition. And it's a bunch of questions where once you have the answer, it's like easy to verify the answer, but it would actually take a pretty long time to try to solve one of these problems. An example would be like, here are a bunch of constraints for like a soccer match, and then find the match that actually fits all those constraints. We actually asked a lot of humans to do these questions. And on average, some questions took, I don't know, like more than 2 hours for a human to solve. And then many of the questions, if you look at this scale, it's like a lot more questions humans were unable to solve in 2 hours versus the ones that they actually solved. But you can see deep research model from OpenAI can solve around half of them. So pretty good progress. OK, so to summarize, you should sort of see intelligence as sort of this commodity. Jason, do you want the newest code?
I think we're good.
OK.
Thank
you. So intelligence as a commodity. Once we sort of achieved abilities with AI, the cost of it will be driven towards zero. I think the trend will continue. The idea of instant knowledge, so anything that's sort of publicly available information, you'll be able to get access to that instantly. And maybe a few implications here. So one is sort of democratization of fields that were like previously gated by like kind of arbitrary barriers of entry based on knowledge. Coding is definitely one, like vibe coding is a great example. Personal health is maybe another. So like in the past, let's say like you wanted to sort of do biohacking experiments. You like go to the doctor and then you're like, oh, well, I want to improve like say my nasal breathing. And then they're like, well, you should just try the thing I told you. And they like wouldn't really help you understand like what do you need to do to like do your own experiment. But now ChatGPT can almost give you any information that like a pretty good doctor could give you. Another implication is like slightly higher relative value of private insider information. So given that the relative cost of any public information is now a lot lower, there's sort of the skew where like the relative price of private information is now going to be a lot higher. So like, let's say houses that are not on the market that can be sold. Well, now that information is more valuable. And then finally, I think we're just going to have like frictionless access to information eventually. And instead of accessing an internet that's sort of public to everyone, you'll get your personalized internet where like, whatever you want to know, there'll be like a personalized website to show you that. Okay, second idea, which is asymmetry of verification and verifier's law. So asymmetry of verification, obviously a very common idea in computer science, which is basically that for some tasks, it's much easier to verify a solution than to find the solution. So here are some examples. So Sudoku, very difficult to solve, but it's easy to verify if you have the answer. Another one is like, say, writing the code to run Twitter. Obviously, it takes like a team of, I don't know, thousands of engineers, maybe hundreds of Elons running the company, to generate the website. But to verify that it's working, it's like a lot easier. You just have to render it and click around. Competition math problems. This is a case where I would say some of them, it's like just as easy to solve as it is easy or hard to solve as to verify. So that's like a sort of middle case. Data processing code, I would say, is sometimes a different case. So like, if you want to do some script, like process some data, I think it's pretty easy to write it. But then like, if you give me someone else's messy code, it might actually take longer for me to like figure out what their code is doing than for me to write my own code or to check their code. Writing a factual essay. This is another example where I think it's pretty easy to make like feasibly true claims, but then like fact checking a particular claim might be extremely tedious. So that's one example where you have like the opposite asymmetry, where it's easy to generate like a feasibly true essay, but it takes a lot longer to verify that it's a good essay. And then this even extends like this idea to things like creating a new diet. So I can assert that the best diet is to only eat bison, which only took me like 10 seconds to assert. But if you want to verify whether this is actually a true claim, then you would need like a large sample size, and you have to wait for like long-term outcomes, and it might be noisy. So this is just a few examples of like asymmetry of verification and where tasks are on this sort of spectrum. And you can sort of visualize it like this. So x-axis is how easy it is to generate, and then y-axis is how easy it is to verify. So you could see, let's see, Sudoku is like pretty, let's say like medium difficulty to generate, but easy to verify. Twitter is obviously hard to generate, easier to verify. Best diet, easy to generate, hard to verify. And then you have things like sort of in the middle, as I mentioned. And then the interesting thing I want to point out here is that you can actually improve where like a task is on this plane by giving privileged information. So for example, in competition math, if I provide you with an answer key, then suddenly checking it is very easy. Or if you're writing code and I give you the test cases, as we do in SweBench, then checking it also becomes very easy. So the idea here is there are certain tasks where you can do some work beforehand and increase the asymmetry of verification. So that brings us to this idea that I'm calling verifier's law, or if the word law like triggers you as a scientist, you can call it verifier's rule. But basically, the claim that I'd like to assert is that the ability to train AI to solve a task is basically proportional to how easily verifiable the task is. And the implication is any solvable, easily verifiable task will eventually be conquered by AI. And to be a little more concrete, verifiability, I would say, is a function of these 5 things. So 1, is there objective truth to what's a good response and what's a bad response? 2, how fast is it to verify? 3, can you verify, like, say, 1 million different proposed responses at once? 4, is there low noise? And 5, do you get a continuous reward? So do you differentiate only between passing and non-passing, or do you give like the entire spectrum of response quality? I guess most AI benchmarks by definition are easy to verify, and that's like a nice instantiation of verifier's law where you can see like, okay, all the benchmarks that we've cared about in sort of the past 5 years have been solved by AI relatively quickly. Okay. One sort of great example of leveraging asymmetry of verification, encourage you all to take a look if you haven't read this yet, would be AlphaEvolve from DeepMind. Basically, they were able to solve these like tasks that fit this asymmetry of verification by just spending a lot of compute via sampling and like a smart algorithm. And it includes a bunch of tasks in like math and like optimizing usage of compute, et cetera. A sort of example of this is this, you can come up with like math problems like this where it's like find the placement of these 11 hexagons where you can draw like the smallest outer hexagon around it. And then you could see like something like this clearly satisfies like all 5 criteria here. So it's objective, you can just plot it to check the answer. It's scalable to check because it's computational. It's low noise, you're going to get the same result every time you check it. And then it's continuous reward. So the size of the hexagon gives you directly like a measure of which answer is better than another answer. How the algorithm works, you should read the paper, but I'll just give you like maybe a 1-minute overview. So basically they take a large language model. They sample a bunch of candidate solutions. So like some of them might be good, some might be bad. They grade it because they have a way of grading it by definition of the task that they choose. And then they take the best one and they feed it into that large language model for the next round of sampling, sort of as inspiration. And basically, once you spend a lot of compute and iterations doing this, you can see this is just one example they had in their blog post that the performance or like how well you're doing the task obviously increases over time. And sort of the smart thing that they did here is that they sort of sidestep. So like, for most of deep learning, we just care about, like we mostly cared about generalization from training to test. There's like 2 forms of this. One is like same task, but unseen example. Another one is like unseen task. But here they pick problems where train and test are the same. So you just actually just want to know the answer to a single particular problem. And that allows you to sidestep like a lot of these issues. And so you kind of have to pick problems where you can possibly get a better answer than what you already know. Okay, so to summarize, asymmetry of verification, whenever you have a task, I would recommend thinking about where it is on this plane of asymmetry. Verifier's law or rule states that anything that's very easy to verify will eventually be solved by AI. Evaluation benchmarks and AlphaEvolve are some examples of this. Some implications. I think one is going to be that the first tasks that will be automated are those that are very trivial to verify. And then the second is, I think one of the sort of nascent areas, like if you want to make a company, or I think that is going to grow, is like coming up with ways to measure things that then can be optimized by AI. Okay, last thing, the jagged edge of intelligence. So if you ask like how AI will change the world, I think people have pretty different views. So this is from earlier this year, but like one of my ex-colleagues, Boaz, says that East Coasters underestimate sort of the magnitude of change that's going to come, and they're sort of like, oh, the current model can't do this. They don't think about the trajectory as much. Whereas in the Bay Area, maybe we underestimate some of the like friction and time lag it takes to deploy some of the models that we've trained. Another one, Rune, who I like and you should follow if you don't, says that nobody should give or receive any career advice right now. Everyone has broadly underestimated the scope and scale of change and the high variance of your future. Your L4 engineer buddy at Meta telling you, bro, CS degrees are cooked, doesn't know shit. So there's clearly a wide range of opinion on how AI is going to affect different industries. One sort of hypothesis that's been around for a long time is this idea of a fast takeoff. So it's basically like, once you pass humans in like a certain, like once you achieve this certain thing, then you'll like suddenly become much, much stronger than humans. So like you'll have this like takeoff duration where in a short amount of time, you gain this like huge amount of intelligence. I would say that this is probably not going to happen, and I will tell you why. So fast takeoff, maybe this is like a simplistic version of their argument, would basically be like, for many years you can't train GPT n+1 with the AI, and then in year 2 you can suddenly do it. But I think it would be more like something like this, where every year you like make gradual progress towards AI being able to self-improve. So like maybe year 0 you can't even get the code base running. Halfway through year 0 you can like sort of train something, but the result isn't really amazing. And then maybe after that it like trains autonomously, but like it's not as good as if you gave it to like the 10 best researchers you know. And then like maybe sometimes you still need humans to intervene once in a while to get it to continue running well. So I think it's more of like a spectrum of self-improvement ability rather than like a binary like, after you achieve this one thing, then you can suddenly create superintelligence. Another sort of reason is that I believe the self-improvement rate should be looked at in like a per task fashion. So you can think of like there being like a spectrum of different tasks. And you can sort of like think of it like this. So there's like some jagged edge, right? So at the peaks, you have like problems that we can currently do especially well, like hard math problems, some types of like competition coding. And then there are like also these valleys that are like a little bit weird. So like, for example, for a long time, ChatGPT would say that 9.11 was greater than 9.9. And then you have things like, speaking Tlingit, which is like a language I think only a few hundred Native Americans can speak. I do not think ChatGPT can do that well. And I don't think we'll be in this case where like, you have a self-improving model and then suddenly you can do everything well. I think you're more likely to be in this case on the right, which is that like every task will have a different rate of improvement. So like maybe some tasks improve a lot because they're verifiable and you come up with an algorithm that can improve those tasks quickly. And then other tasks like speaking Tlingit, which is maybe bottlenecked on like you going to like a Native American reservation and like, documenting like what the language is. I don't think those tasks will improve as quickly. So I will say a few heuristics for like how to think about how fast AI will improve at certain tasks. So one is I think AI is good at digital tasks. So I don't know, like this homework machine comic is actually like pretty accurate given that it was created in 1981 for like how AI works. But iRobot, obviously we don't have, well, maybe we'll have that soon, but we don't have that yet. I think the core reason why development of AI has been so much faster on digital tasks is just iteration speed, because when you're doing a digital task, you can scale up compute a lot more easily than like you can scale up experiments using a real robot. Another kind of obvious one is that tasks that are easier for humans tend to be easier for AI, so you can have like a spectrum of how hard things are for a human. One sort of thing that I think is coming is sort of ability to do tasks that maybe humans can't do because of maybe fundamental limitations that we have as like humans with like a biological brain. So maybe, for example, predicting the occurrence of breast cancer is a task that is possible if you can, like, let's say if you've read 10 million images of breast cancer, you could find like the one pattern that allows you to predict it. But as humans, we don't like live long enough or have enough attention to do that. Another extremely simple heuristic is that AI tends to thrive when data is abundant. So you can think of here's just a very clear example where you can look at math performance of language models in different languages. And if you plot the frequency of that language, in other words, how much data we have versus performance, it's a pretty clear trend that the more data you have, the better you're going to do on that task. And then maybe a special unlock or exception to that rule is if you have a single objective metric, then you can do sort of the alpha evolve or alpha zero tactic where you can generate essentially synthetic data via reinforcement learning. So my former colleague Danny Doe, he had this nice tweet: any benchmark can be rapidly solved as long as the task provides a clear evaluation metric that can be used as a reward signal during fine-tuning. Yeah, and I have this table that I've shown before of you can just sort of use these three heuristics to predict when AI will be able to do certain things. So you can say translation top 50 languages, easy, already done. Debugging basic code, did in 2023, I would say, and it's something that's medium difficulty for humans, digital, easy to get data. Competition math, hard for humans, but digital and easy to get data, so done in 2024. Conducting AI research, hard for humans and digital, but not super easy to get or create data, so I would say maybe 2027. I'm just making up numbers here. Chemistry research is also hard for humans, but it's not digital, so I would say probably later than AI research. Making a movie, very hard for humans, but digital and easy to get data, so maybe 2029. Stock market prediction, very hard for humans, digital and easy to get data, so I'm not really sure about this one. Translation to Tlingit, easy for humans that know how to do it. Digital, but not very easy to get data, so I would say probably pretty low chance that AI will be able to do this. Fixture plumbing, I would say, yeah, medium difficulty for humans, but it's not digital. Easy to get data, not really sure. Hairdressing is another one that I think will be pretty hard for AI. And then if you get to the really hard ones, for example, traditional Uzbek carpet making, very hard for humans. It takes a team of people a month to make a rug. Not digital, not easy to get data. I don't think AI will do this anytime soon. Taking a girlfriend on a date that she's happy with, impossible, not digital, not easy to get data. So I don't think we'll have this. I think we'll be in business for a while. Okay, so to summarize, the jagged edge of intelligence. I don't think there will be a sort of fast superintelligence takeoff because every sort of task has a different capability and rate of improvement. The impact of AI will be largest on tasks that meet certain properties, namely they're digital, easy for humans, and data abundant. Okay, so for implications, I think certain fields will be extremely heavily accelerated by AI. So, software development is obviously one of those. And then other fields will probably remain untouched, like hairdressing. Okay, great. So, in summary, intelligence and knowledge will become fast and cheap. Number 2, verifier's law. Measurement is a driving factor of AI progress. And then finally, the edge of intelligence is jagged. Okay, great. I will end here. I have a feedback form if you want to give feedback on my talk. I will read it. And yeah, happy to connect over Twitter.